Let's start today's session. Before that, let us recap what we studied in the previous class. So in the previous class, we started with the switch power dissipation. So in that, whatever things we are saying in the previous class, we done something like the switching activity of the static gates we seen, like if both the inputs are independent. So how we can, if the input get are the output of the static gates depends on the function. If you are realizing with the like function a comma b for the basic gates example, like one more scenario, if I take, if the inputs are independent to each other, then what about the probability of occurrence of 0 and 1 is same, because we may get the output in the basic kit either 0 or 1 only will go. So from that we studied like what will be the switching activity or the transition, the probability of occurrence 0 and the probability occurrence of 1. So that we seen. Next, same the way for n number of input, what will be the general formula that we seen. Next, the second case is like we have seen, if the number of inputs gets increases for NAND gate and NOR gate, automatically what will happen, the switching activity will be reduced. So that we are seeing. So from the examples, next thing is like how the switching activity will be there for complex logic gates, even that we've seen for a large value of n, because that is little bit complex will be there. From that we calculated the switching power dissipation. We added in that additional factor as the switching activity factor, that we can call it as alpha. That is nothing but limit n tends to infinity n of n by n. So now here we are seeing the total the switching power dissipation. Here will be our dynamic power dissipation. Here we see like the alpha naught CL VDD square, the clock frequency plus the summation I is equal to 1 to k alpha I CI VDD clock frequency. And here we seen the alpha naught is nothing but the switching activity at the output node, and the alpha is nothing but the switching activity at the ith node, like internal node I can say. Then we seen if the inputs are not equiprobable, that meaning is what the probability of occurrence is not same, then what will be the formula that we have seen. Next, if the inputs are mutually dependent, then what happened? So that also we are seeing here, like without reconvergent fan out and with reconvergent fan out. Like here we are having 4 input. So here this gates it is driving this signal, like you see the E and F is driving the another one more NOR gate, then the G will get same only, just here also the another without reconvergence here. So simple, like we are given the B and C shorter, even though if you do like this the input will be x1 x2, but here we are having 4 inputs. See this panel. So that is what we've seen in the previous classes. So now what we'll do, let us study from this class. To study the transition probability in dynamic gate. Okay. Now, earlier the logic style has a strong influence on the node transition probability. So for static Cmos, already we calculated the transition probability. So example for static Cmos, already we calculated the for static Cmos, the transition probability is what is that? P0, that is P1 will be is equal to P0 into 1 minus P0, that is transition P0 to 1 actually. This is what for static CMOS. Now in case of for dynamic CMOS now, because as I said earlier, the difference between the static CMOS and the dynamic CMOS, at the same time we are saying like how many the number of transistors is required to design the static CMOS circuits and the dynamic CMOS circuits. Now if I say the dynamic CMOS or dynamic gates, the situation will be different here, because we can take an example for dynamic CMOS circuits. The example what I can take in the sense, let me take the example circuit. Already you might have studied in the CMOS VLSI. What is the circuit I can say called as example is NORA logic circuit. NORA. So you might have studied dynamic CMOS logic will be like we have the PMOS in the top and the NMOS in the bottom. In middle you have either P network or the NMOS network, right? So narrow logic does the same thing only, but additionally we'll have the cascaded, like it will drive the another one. Say example, if I want to say narrow logic circuit will be like this. Let me draw that here. PMOS. This will be your NMOS network, that is network is NMOS network or PMOS network, okay. Then here is NMOS, then it will be connected like this, then this will be your clock. So here we will apply the inputs, then NMOS means you take the output here, right, output. This will be your VDD. Now again I will have the PMOS here. Here I will have the network as PMOS network. Then again one more NMOS. This. See, now you can see this is also clock. See, all the clocks are synchronous to each other. Now what happened? This output is right, so this will drive this network. VDD SS, then this is PMOS cutter, right? So output will be taken here. This is the general network. Now what I will do, I will draw a NORA logic CMOS inverter. CMOS inverter using NORA. So how it will be same inverter in the sense we will have only one input, right? So this is PMOS, here NMOS network. So NMOS, then here this NMOS. So this will be your clock. Okay. Now this will be your VIN, your VDD, then VSS. Now the output you have to take it from here, right? Again here the input here. So here PMOS, again here is PMOS actually. NMOS. See, this will be a clock, same clock only. Now we have to connect this portion to here, like this you have to do. But the output, this is VDD, this is VSS. Output where you have to take? For NMOS will take output will be in the top. For PMOS you have to take output at the bottom actually. So this will be your output. Now you have to remember something like here we are having a load capacitance because dynamic, right? Then here we are having the dynamic capacitance, that is CL. Then here also we may have one capacitance, that is internal capacitance, that is C1. Even here also you may have capacitance C2 actually. These all are internal capacitance. This is load capacitance. Now, when you are going for a dynamic case, first initially what will happen, the output will be recharged, or I can say the mode of operation. Mode of operation will be two ways. The one is recharge phase. Recharge phase. The second one is evaluation phase. We need to know when it will be pre-charge, when it will be evaluation. Pre-charge in the sense the capacity, the load capacity has to be pre-charged during the time, even though if a input is changing, it won't evaluate. But so when the circuit will be evaluated during the evaluation phase, so means pre-charge phase in the sense when means clock will be is equal to 0. When the clock is equal to 1, it will be in the evaluation phase. So how can I draw the diagram now? So very simple. You can say, see, this is my clock, correct? So now this will be recharge phase, this will be evaluation phase. So in this way only here it will work. So I am applying the clock to the input here. That is clock, or I can say 5. We will apply. Okay. When I go to apply, clock is equal to 0 in this circuit. Let me say clock is equal to, that is during pre-charge phase. What will happen now? During pre-charge phase, that is clock will be is equal to 0. Now you have to say, I have not applied any input. Assume input Vin is equal to 0. Or apply, okay. Vin is equal to 0 volt. Even the Vin is equal to 0. So example I will say the input is equal to 0 here. Okay. Now when clock is equal to 0, so this will be on, correct? Means Cmos is on. Then automatically what will happen? So there will be a voltage, it will go over there, then the capacitance will be charged completely. If the capacitor charged completely, even though you need to think about the clock 0, if the same, like because it's a synchronous clock, when it is a synchronous clock, clock is equal to 0, even this also will be on, correct? So if it is on, so what will happen? The VDD will flow it until here, you can see. So when the VDD flow is completely charged in the, so how much voltage will be here? Around 5 volt, correct? If it is 5 volt, the PMOS is having 5 volt, the PMOS is off. So the VDD will be charged, so I will get the output here. Now it's not evaluating. When I give the input is equal to 0, I am not getting anything as of now. So at that time, what will be your output? So you may think, so here I pre-charged, but what about this stage? You will have the question about this stage, correct? So means initially all the capacitors will be discharged, or I can say initially if I have not done anything, it will be completely, it will be pre-charged. So now what will happen when input is equal to 0? So what will happen? It is pre-charged. In the sense initially assume that it is pre-charged. Means I am having 5 volt. You have to assume that all of it is 5 charged. Okay. Means all that it is pre-charged in the sense if when I apply that is equal to 0 only, I am thinking it is pre-charged. If I apply straight away is 1, you have to assume that it is already pre-charged. Right? Now what you do? We need to go for the evaluation phase. So when I go for the evaluation phase, so during evaluation phase, means what? Clock is equal to 1 means like the outputs output node will be discharged. Output node is discharge. In essence, now if I give clock is equal to 1, okay, now if I give as 1 what happen, this will get us off. Now this will become on. If this is on, so your input is 0 only, it won't perform any operation. Remember, during the pre-charge operation, it won't perform anything. During the evaluation phase only, it will perform. During the evaluation phase, even though if your input is continuously changing, so when it will be evaluated? During the evaluation phase only, it will be there. So now when I giving 1, this will be on. So already this was pre-charged. What will happen? It is pre-charged in the sense, initially the capacitor is pre-charged. That is the meaning. Note. I can make a note. Initially the CL is pre-charged. So what will happen? This will be discharged. So I'll get as 0. Now you can see, meanwhile, if I'm giving the synchronous clock, what will happen? Even though when I have some 5 volt, when it is getting discharging, if I get it 0, automatically what will happen? This transistor will also be turned on. If this is also turned on, automatically what will happen? How much of charges there here? The same, it will start to flow over there here. So it will, even this clock is 1, right? This clock also is equal to 1. So when it is get 0, this will be on, even this also on, then even this also will start to discharge. Right? So now this will be nothing but domino phase, or I can say Nora phase, we can say. Now very simple, I can say Nora, the dynamic logic circuit, how it will work in the sense, it will work in the mode of 2 modes. The one is pre-charge phase, second is evaluation phase. During the pre-charge phase, during the pre-charge phase, the output nodes will be pre-charged to a high level. So in this initially the output change, this will be high level, both are will be in the 5 volt. After that, during the evaluation phase, this will be discharged. So depending on the outcome evaluation. So how can I say now the transition probability? So I can say the transition probability about the output, the transition probability will depend on the signal probability. Signal probability, that is P naught. Now what is the transition like? B is equal to P naught. So now where the P naught is probability for the output. Probability for the output as in the 0 state. For n independent, for n independent inputs to a gate, so what will be P1 is equal to, for n input gate, so m naught divided by 2 to the power n, where n naught is the number of entries in the truth table. In the truth table. So now I can say how for let us put some transition activity for dynamic gates. Okay, tabular column. So for inverter, the switching activity from 0 to 1, the property it's a 1 by 2. You can see n naught by 2 power n, so it will be very easy. Next step. So for 2 input NOR gate, now switching activity P0 to 1 is 2 input NOR gate. So number of entries will be 4, right? So possibility here only 1. So we mentioned that it is like only one state, the 0 state only we said, that is nothing but 3 by 4 NOR gate. Because what is the truth of NOR gate? When any both are 0, output will be 1. If any one of input is output is 0. So we mentioned here the probability of output is in the 0 state only we are taking. So 3 zeros will get. So next, for 2 input NAND gate, what will be? Like it will become as instead of 3 by 4, 1 by 4 will come, because the 0 will be, if both are high, it will be 0, rest of the values will be 1. So this is the transition activity. So now here, so you may think why we are taking only 0, because the reason is, so you may think we have the compared to the static Cmos, here the transition probabilities of more. You may ask the question, why only 0, why not 1 state? Okay, why you are considering only 0, why not 1? The reason is, what's the reason? The reason is the output is always pre-charged to 1. So that is P1 is equal to 1 always. Already we've seen this. So that is the reason we took only the. So from this we note that the switching activity for NAND and the NOR gate is more in the dynamic gate than the static gate. So from this we can make a note. Switching activity for NAND and NOR more in dynamic than static, because you can check the previous tables and all. Okay, so now next we are entering into the important thing, the power dissipation. Power dissipation due to charge sharing. This is one of the very important concept. Power dissipation due to charge sharing. Moreover, so in the case of dynamic gate, the power dissipation will take place due to the phenomenon of charge sharing, even when the output is not 0 at the time of evaluation. The output load capacitance is not discharged, but some part of the charge of the load capacitance might get redistributed. So what is the meaning of that in the sense? Let me take an example circuit as 3 input non-dynamic gate. Okay, so 3 input non-dynamic gate in the sense, first we will have the top is here, we will have the PMOS. Then here we have to draw the NMOS circuit. Let me draw the NMOS circuit. It's a NAND gate, right? NAND gate means NMOS. If I go for a NMOS network means NAND gate is series. 1, 2, 3. Correct? Next is here. Okay. So this will be your clock. Now we will have 1, 2, 3. So A, B, C. Okay, so where is the output? Where you have to take the output? If it is a network is like this, either down or top. The output, if it is NMOS, if I use NMOS, the output has to be taken from the top. That is here. This is the output, right? So the output will have one load capacitance. This is your V out. Okay, now you may think, where is the internal nodes? See, where is the internal capacitance? Now I'll say the internal capacitance are here. 1, 2, 3. Let me name as C1, C2, C3. Okay, so now let us say the operation here. It's a dynamic gate. So dynamic gate in the sense very simple. I can say 2 modes of operation. The first phase is nothing but what? It is a pre-charge phase. Second one is evaluation phase. So when it will be in pre-charge phase, during the pre-charge phase, the output node will be charged fully. Means when clock is equal to 0. See here, I will draw clock like this. This is 0, this is 1. When clock is equal to 0, what will happen? Your PMOS will be on, then VDD with relay over there. This will be charged completely, correct? Say example during 0. So irrespective of the input of ABC. Okay. Now what I'm doing, I'm going to apply the input as 1, 1, 0. This is my input. Or first I will apply the input is 1. Example. First I will apply all or 1. When I apply all or 1, what will happen? This transistor is on, correct? This also it is on, then this also it will be on. If all the transistors also is on, what will happen? So like during the evaluation phase, even though one if I give, so what will happen? So this transistor is not on, so there is no way, or it won't perform anything, right? It won't evaluate. Now during the evaluation phase, you think, during the evaluation phase what will happen? Even this will be 1, this will be off, so then it will be try to discharge completely. Even this is also on, I will get a 0 will get. So NAND gate, all the inputs are high, output will be 0. Okay, the second case, what will be their input? First I applied the input ABC as 1, 1, 1, then I will get V out is equal to 0. Right? or I will say transistor T1. This is T1 or Q1. T1, this is T2, this is T3. So due to that T1, T2, T3 all are on during the pre-charge phase. Example, okay, during the evaluation phase what will happen, it will try to discharge, will get Vout is equal to 0. Okay, now the second scenario, I will apply ABC is equal to 1 1 0. Now I am going to change the input 1 1 0. What will happen, this both are on, this is not off. So the pre-charge phase already over now. Okay, so still now it's the evaluate mode only. I am changing the input. So now you have to assume it's the evaluation mode. So it's in the evaluation mode in the sense this is on, this is off. I can say that Q1 or I can take P1, this is N1. So during the evaluation phase the P1 is off, the N1 is on. Now see clearly here what will happen, the capacitance, the amount of charge will be the CLVDT, right? Example here, this will try to discharge. Okay, so when it's try to discharge, it will start try to discharge. Okay, now how much will be here, the value will be VDD because completely fully charged. Now when it's try to discharge over through this, what will happen here, I will get the value as VDD minus VDH. So this capacitor will be charged. How much will be charged? VD minus VTH. Again still here this capacitor also will be charged, VDD minus VTH. After that you can see this capacitor also will be charged. No, because here input is 0. So this will be charged. So now you can see this is started to discharge. Okay, this is started to discharge. So what will happen completely when it is get discharged, this will be 0, output will be 0. So this charge is redistributed, or I can say the charge is in this place, its charge is sharing. This is called as power dissipation. Charge sharing will happen due to this transistor is 0. So this charge will be sharing to the internal capacitance C1 and C2, right? So now during the time when it discharges, again it will go back to pre-charge mode. Again it will be charged fully. So very simple, I can say, even though when the output is not 0 at the time of evaluation also, the output load capacitance is not discharged. So now what you will do, so after the charge is sharing, so like it started to charge sharing, right? Now we need to say what will be the new voltage level here in the output. We need to check, yeah, we need to find out. So that is what we are going to do now. So now, so let me put a condition, or let me put a right. After charge sharing, and the new voltage or new level, the new voltage level is okay. Now what will be that? So I will say first from that I will write as the internal capacitance are like C1 plus C2 plus C3, because 3 internal capacitance are there, into the new voltages V new will be is equal to VDD into CL. This VDD into CL is nothing but your output side. This is nothing but your input, right? So the charge, so it's a, or I will say from this what is the new, the new will be is equal to VDD into CL divided by C1 plus C2 plus C3. This is equation number 1. I consider this equation number 2. We knew. But therefore we need to know what is the change in voltage. Okay, the change of voltage, that is del V. Is nothing but VDD minus the V new voltage only. How much the change in voltage? That is del V actually. So now what we have to do? So we need to find out the del V. So the del V is nothing but del V is equal to VDD minus what is the V new? V new is this VDD into CL divided by C1 plus C2 plus C3. Okay, so now this you can say equation number 4, this you can say equation number 5. Now the power supply transferred from the power transferred, right? The power transferred from the supply that is P, right? What is P? The formula we know. P is nothing but CL into VDD into CL into VDD into del V. So now SB is equal to CL into VDD into the del V is VDD minus VDD into CL divided by C1 plus C2 plus C3. Now do the simplification of this. When I do the after simplification, we'll get CL into C1 plus C2 divided by C1 plus C2 plus CL into VDD square. Now I can say that the new del V actually will become as like this. Change in voltage, like del V will become C1 plus C2 divided by C1 plus C2 plus CL into VDD. This is del V actually. After you simplify the del V, you may get this. So from this I can say the power is additional to the normal switching activity power dissipation. Yes, this is about the switching power dissipation. So these all are will belong to the switching power dissipation. Next, what we will do, we will study about the short circuit power dissipation. Next, we will go for short circuit power dissipation. Next we are going to study about short circuit power dissipation. So what is meant by short circuit power dissipation? It is nothing but as the input changes slowly, or I can say due to the input is short, that is slowly power dissipation takes place even when there is no load or parasitic capacitor. So as the input changes very slowly, the power dissipation will takes place even when there is no load or there is no parasitic capacitance. No load means there is no load capacitance or the internal capacitance, the parasitic capacitance also. That is what we can say it's a short circuit power dissipation. So this will happen due to rise time and the fall time. So when there are some finite rise time and the fall time at the input of Cmos logic gates, the both the MOS both the PMOS and the NMOS transistors are simultaneously on for some certain durations. Like say example, if I want to say in the CMOS inverter, when the both the transistors will be in on, V in will be is equal to VDD by 2. At that time both the transistors are on, I can say. Correct. So on that is some certain duration. So shorten the power supply line to the ground, that will leads to current flow from supply to the ground. So when, so example I can say when Vn is equal to VDD by 2. Example I am taking the CMOS inverter. Okay. When Vn is equal to VDD by 2, then what will happen? PMOS also on, NMOS also on. If both are on, then what will happen? Then there will be a direct, or I can say direct path between VDD to ground. So this yields the current flow from supply to ground. That is called as, this is the power supply. Short circuit power dissipation. So the short circuit power dissipation takes place for the input range in the way, if I want to say in the terms of formula, like say example, your input voltage will be less than threshold voltage VTN. Next, your input voltage should be greater than VDD minus VT. So at this case, short circuit power will takes place. So during this time only both P also on and N also on. That is what I said earlier. Now let us analyze this. So let us estimate the average circuit current. So to estimate the average short circuit current, always we know that, so this will happen when, then one more thing I want to say, when it will happen actually, this one, these things, when the PMOS and the Nmos will be in which region? Saturation region. P also will be in saturation. Nmos also will be in the saturation. So to estimate the average short circuit current, let us consider the Cmos inverter circuit. Okay, let us draw the Cmos inverter circuit first. So for all the cases we are taking the example as Cmos inverter only. Begin, then VDD, then here VSS, so you may think what is IC, right? See, very simple. This is what I can see short circuit current. Now the output you have to take, right? Output will have one constant, that is L. This will be your V out. When I apply input as like this, output I will get as like this. So where this will get happen actually, this will happen during the rise time and the fall time. We should know what is the rise time and the fall time, right? Okay, let me put. Okay, so now which is the rise time and which is the fall time in the sense. So here this is I can call as rise time. This I can call as fall time. This I will call as fall time. Means simple, I can say 10% of from 0 to 1. 90 10% of 0 to 1. Sorry, 10 to, sorry, not 10%, 10 to 90%. Same here also, 90 to 10%. Like falling is from, will happen from 1 to 0. So the time taken from 10 to 90%, that one is I think the rise time, fall time is. So during this time actually there will be some short during that time actually, right? So gradually when it is getting increases, this transistor also will be on, this also transistor will be on. So automatically what will happen, there will be a direct path from VDD to VS, or there will be some short circuit. Now what we need to do, we need to assume so now we need to, let us assume that tau, right? This tau is both rise and fall times of the input. So what I'm going to do in the sense, like I make that tau r is equal to tau of is equal to tau. I'm going to say the equal rise time and the fall time. So you can say this is 0, you can say this is 5, so you can say this is also like around 15, then this is 20 nanoseconds. Okay, that is all. And the inverter is symmetric. Means what the amount of rise time is there, the same amount of time only will be there for fall time also. So and inverter is symmetric. So Inverter is symmetric in the sense we'll have the one more parameter, that is a process dependent parameter. That is, the inverter is symmetric. The beta n is equal to beta p is equal to beta, where beta is a process dependent parameter. What is the formula? You know that what is the formula for beta? Where the beta will be is equal to mu into C naught x into W by L. If it is for Nmas means, so Bn, like Bn means mobility, mu1 Cox W and L n. Then for Pmas will be beta P will be is equal to mu P mobility for Pmas, then Cox, then W by L, where Cox is nothing but a oxide capacitance. What is the oxide capacitance? That also we need to know, right? Where the Cox will be is equal to epsilon ox divided by Tox, where epsilon ox is equal to epsilon into epsilon r. These are the parameters like this will be there. So that is why I said that this is a process dependent parameter. So the beta will be dependent on the mobility, the oxide capacitance. The oxide capacitance nothing but like epsilon of the permittivity, the permeability of silicon by the oxide thickness, then the width and length of the transistor, W by L n W by Np. So this only we are taking as beta. Yes, that is the one thing. And threshold voltage. As we know that for NMOS the threshold voltage is positive, for PMOS the threshold voltage is negative. So this we are going to take as VT. Simple. VTN is equal to minus VTP, that we are going to consider as VT. These are the parameters we have taken. Now first we need to find out the mean short circuit. I have no load attached. Okay, so let us find mean, that is the mean current. Okay, the mean short circuit current, that is nothing but I mean of the inverter having no load attached. So let us write I mean. Okay, the I mean is equal to, like it is symmetric I said, right? So area will be 2 into 1 by the time period, the whole time period, because if I take one clock cycle rise time fall time 1 t, so 1 by t. So I am going to take both the places, right? The first is nothing but the t1 to t2. You may think, right, how to write this, right? So what I will do, better instead of writing this, I'll do something. Okay, so let me draw the diagram first, like the input and output, the transient response of your inverter. Let me draw. First, I will draw the input. This is your input. Okay, then let me draw the output. this is 0, right? So if it is 0 in the sense, the output will be like the 1 will come, okay, then 0, then will be like this, then will be like this, then this, okay. Now we can say, you can say this is T1, okay. So I will say this will be your T1, this is, I will consider as T2, no, not T2, this is, I will consider T2, center part also I will take, because as I mentioned, okay, this one as well as even this also. T2 I will take this, this is T3, same the way, this is T4, T5, this is T6. Now we need to see about the current, correct? So like I will take here one x-axis here. Now we can say, let me draw as the input gets like here the input is increases. As the input is increases, what will happen? Here the current also will increases, then the current will get decrease after that in this place, right? Same the way even here also the current will increases, the current will be decreases here. This is nothing but your ideas. Now this will be your V out. Now we can say this T1. This T1 is nothing but, I want to write, what is this T1? This T1 is nothing but, what is this T1? That is nothing but here you have to assume as it is a threshold voltage. Because when the transistor is on minimum voltage, right? Threshold voltage, you assume threshold. What is the T2? The T2 is nothing but your input like VDD by 2. Okay, so 2.5. See here simple I can say this portion is, I'll say the simple, very simple I'll say this is 0, this will be your threshold voltage, this is 0.7 divided by 2 means 2.5, then this will be your VDD minus VTH means we sound 4.3 I can take, this will be your 5 volt. So when the input reaches VDD by 2, the current will be in passive situation. After that what will happen? You get reduced, right? It's a Cmos inverter. You might have studied the VI characteristics curve and all, right? So same thing, whatever we done here, same the symmetry, it will be symmetry same even here also. What is the T3? As I mentioned here, the T3 is nothing but VDD minus VTP. VDD minus VTP. Right? Now we can see here something I will show. This place, this one is nothing but this place is nothing but your, that is minimum current, that is minimum current. This is your, this is the maximum. Which one? This place nothing but it's a peak current. That is maximum current I can say. Minimum current and the peak current. Okay. Now I will write the expression. That is I mean. Okay. So the I mean, that is the current, the mean current will be 2 times of, because 1 by T. Now you can see the integral T1 to T2 first. You take the T1 to T2, we'll have one current, right? That is I of T into dt plus. Next we will have the another current, that is T2 to T3, I of T into dt. This is your first transition. Okay, so same thing will happen for the second transition also. That is why we mentioned like symmetry we said, right? So this I will consider equation number 1. Because of symmetry, we can write as, what is I mean now? 2 times, right? So this will become as 2 times of that, 2 times of that, 2 by t into, right, 2 times of 2 by t into, that is 2 by t into, then as I mentioned, you remember in the previously, the t1 is equal to the t2, t1, t2 mentioned, right? t1, t2, we can see in this graph, t1, t2, t2, t3 is symmetric. So now again it is twice. So that is why what I am going to do, 2 by t, 2 into 2 by t, I am going to take as t1, t2. That is the reason I took twice. So t1, t2, t2, t3 both are same. So we are going to return as like this. So this will become as 4 by t integration t1, t2, I of t into dt. This is equation number 2. Note, as I mentioned earlier, you have to make a note in which region both the transistor is working. As I mentioned earlier, as the NMOS transistor is operating in saturation region. The NMOS is operating in a saturation region. When the NMOS is operating in a saturation region, or you know that when I go for a Cmos inverter, okay, the Cmos inverter, you might have studied some 3 equations for drain current equation, ID equation. So now for saturation region, what is the ID current? For NMOS I can say, so I can write as the IDS will be is equal to beta by 2 into Vn minus Vt, that is VDD. Actually it's supposed to be VDD. VD minus Vt the whole square. This will be for the current 0 less than equal to Is less than is equal to I max. Not equal to, okay. I should be from 0 to I max. So this instead of VDD, actually I can write as beta by 2. We are considering here the input, because for input Vn minus Vt, the whole square, since we know that the Imax, when you will get the Imax will get at your input will be is equal to VDD by 2. So now what you need to do, so let us do the substitution. That is, I will write instead of IDS, I will write as this only as I of t will be is equal to beta by 2. This instead of Vn of t, I will write as, sorry, Vn of t minus Vt the whole square. I will take this equation number 3. Now what you will do? Now substitute the equation number 3 into, substitute equation number 3 in 2. That is I mean. I mean is equal to 4 by t. Before that I need to do some simple like substitutions. Before to do the substitution, let us consider something we need to consider, that is V in of t will be is equal to VDD by tau into t Next, what is T1? The time T1 is nothing but tau by VDD into VT. Then what is tau 2? Tau 2 is nothing but tau by 2. So put all these things in this. Okay. So first, so all substitute in equation 3, not equation 3, in 2 actually. In the 2 equation, substitute the equation number 3 in 2. So what I'll get now? I'll get the equation as I mean is equal to 2 times of beta by 2, because beta is a term, beta by 2, not beta by 2, by t, integration T1. What is it T1? The T1 is nothing but tau by VDD into VT. Tau 2 is nothing but, not tau 2, it is T2, sorry. It is T2, right? T2 is tau by 2. Then inside actually we will have Vn of t minus Vt the whole square. N of t to the whole t. So this will become as equation number 4. Okay. So now what we will do, we need to perform integration. So to make it easy, what we will do, let us substitute or let us consider VDD minus tau into t minus Vt is equal to x. Or I will take like this, okay? Let's substitute. X is equal to VDD by tau into t minus Vt. X is equal to this in the sense, see, I have done something over there. See, V in t is the right. Actually, we have to substitute the Vn of t. What is the Vn of t actually? Already, as I said, the Vn of t is nothing but VDD by tau into t. Yes, this is Vn of t. Yes. So this whole thing we are considered like this, x. If that is the x, then what about dx? Dx will be is equal to VDD by tau into dt. So Vt is a constant term of VD by tau. This is dx. Okay, now we got. If this is changed, automatically the limits also will get changed. Correct? So for lower interval, first, for lower interval, what you'll do? So you have to substitute for the new, because you have to get the new interval. So what you will do? Let us take the lower interval. What is the lower interval actually? In the place of t1, you can see here. Remember, see here the lower interval we are having tau by VDD into Vt. So now we can see that is in the place of what? It is in the place of t actually. Vt, right? Now for two new interval, you take this only, right? X is equal to, see this, take this only. X is equal to VDD by tau into t minus Vt. Now same the way x is because we got the dx, right? X is our new interval, lower interval, that is new. VDD by tau into what is the t? From the integral I can take, that is nothing but tau by VDD into Vt minus Vt. Now what is the x? X will be tau will get cancelled, Vd will get cancelled, Vt minus Vt will get, so will be 0. X is equal to 0 I got. Same for upper interval. So for upper interval, what is the same thing you do? X is equal to VDD minus tau into t minus Vt. Now the upper interval actually VDD by tau into what is the t? T is nothing but tau by 2 minus Vt. Now tau will get cancelled. I'll get the new interval as VDD by 2 minus Vt. This is by x. So now my new interval will become as x is equal to 0 to x is equal to Vd by 2. Now substitute all these things in the equation number. Substitute those above in the equation number. Substitute above in the equation number. Which equation actually? Equation number 4. Like x dx in the sense the new interval, everything substitute. So what I'll get now? I'll get as I mean is equal to 2 beta by t. The lower interval is 0. The upper interval is VDD by 2 minus Vt into, that will become as x square actually, into tau by VDD into dx. Because you can see the earlier why it is x square, because this is VD by t minus VD the whole square. So x square, then dt is nothing but that is dx, right? What is dt here? From this I can take. From this I can take that dt is nothing but tau by VDD into dx. So that is what we substituted here. Okay, now we need to perform the integration. Let us do the integration. 2 beta by t into, this has to be with respect to x. So I can take out the tau by VDD will take out. Then what will happen? X cube by 3, then 0 to VDD by 2 minus Vt. Now again do the simplification. I'll get us 2 beta by t into tau by VDD into upper interval, right? So VDD by 2 minus Vt the whole cube divided by 3 minus 0. So now this will become as 2 beta divided by t into tau by VDD into VDD by 2 minus Vt the whole cube divided by x cube by 3, right? So x cube, x, the total x cube by 3 in the sense, sorry, it is supposed to be what? Okay, 1 by 3 I will take outside. This is 3 now. Yes, this will be the whole cube. Take 1 cube outside. Now let us do the modification. What I will get? Again, 2 beta is equal to, so we can VDD by 2 minus Vt the whole square is nothing but 2 beta t divided by tau by VDD into 1 by 3, right? It is 1 by 3 into VDD minus 2 VT divided by 2, the whole cube. So again this will become as 2 beta divided by T into tau by VDD into 1 by 3 into, this will become as 8, right? VDD minus 2 VT the whole cube divided by 2 cube is 8. So 24. So 2 beta divided by T into tau by VDD into 1 by 24, correct? 1 by 24 VDD minus 2 times of VT the whole cube. Now what will get? 2 beta T to tau by 24 VD VDD minus 2 times of VT the whole cube. So this will become as beta tau divided by 12 VDD beta, this is T, right? Beta T. So I will take this also, right? 2 VDD minus 2 VT into tau by T. So this will be your I mean beta by 12 VDD, VDD into this VD minus 2 VT the whole cube. So I'll take this will be your the expression, fifth expression. I can take it as fifth or sixth expression. Now what is the short circuit power? The short circuit power is, therefore the short circuit power is given by, that is PSC. Short circuit means PS. PSC will be is equal to V into Y. So V is nothing but VDD I mean. So VDD into beta by 12 VDD into VDD minus 2 times of 2 V to the whole cube into tau by T. Then this can be VDD will get cancelled. Then I can say beta by 12 VDD minus 2 times of the VT the whole cube into tau into F. PSC, or otherwise I can write as this PSC is equal to beta by 12. So like I can take the VD as outside. Okay, so if I take VD as outside, then this will become as, once I take VD as outside, VDD cube, then 1 minus 2 VT by VDD the whole cube tau into F. So this also can be considered as final equation. Now we can see the short circuit will be, what happened? It is VDD minus 2 times of VDD the whole cube actually. The tau, and so what are the factors are affecting here for the short circuit power dissipation? So one factor is beta, process dependent parameter. Second, the tau, that is the rise time and the fall time. The third one is something, but you can see the frequency, that is F. So here we can say as the clock frequency will decide this one F, how many times the output changes per second. So from this I can say the power circuit, short circuit power is proportional to frequency, and the short circuit power is proportional to the rise time and fall time, that is tau r and tau f I can say. Then I can say the short circuit current may for different slopes also will be there. Like let me show that figure, like with respect to the timings how it will be, then with respect to the load capacitance also how it will be. So the first figure will be okay. Now you can see this figure 1. This is your figure 1, you consider this is figure 2. What is this in figure 1 showing? This is showing us the short circuit current as a function of input rise and fall time. That is short circuit current, okay, power. Short circuit current means ISC I can say. ISC will be is equal to, is the f of, it is function of rise time and fall time input. Then what about this? This is the variations of short circuit. Variations of short circuit current, that is ISC with load capacitance. Okay, now you can see here what is happening. The first one here, the tau is equal to 1 nanosecond, tau is equal to 2 nanosecond, tau is equal to 5 nanosecond. What has happened here? When the rise time and the fall time get increases, you can see when the rise time and the fall time with the increases, what happened? That is, I can say, if the tau is increases, right? If your increases, what happened the short circuit current? Short circuit current also increases. You can see that it's in the microampere. See, when the rise time is get increases, as it increases, so your ISC also will be increases. That is the first the observation we can make. The second observation you can see based on the CL. Now, as the CL, that is a load capacitance, you can see here, if CL is increases, means see, first the initial the CL is equal to 0. We have not done anything. So automatically what will happen? That is time secant this is the I circuit, capacity load. Next, this will be the dotted line which is showing here. This dotted line which is showing is nothing but a ISC actually. Now the CL is 50 femtofarad, CL is 500 femtofarad, 1 picofarad. So it's keep on increasing. When it's keep on increasing, what happened here? You can see this. You can see this is nothing but time, right? So as the CL values get increases, so from this I can say what happened. Your short circuit. What happened to short circuit? You can see this point. You can see this point. Okay. What happened? The short circuit reduces. Okay, short circuit is bad. What about that time, that tau? Tau will be increases. So this is the very important thing. So when we are having the short circuit, either one thing I can say here, like the short circuit power can also be reduced. How we can reduce this? How we can reduce? How to reduce short circuit power dissipation? By increasing the load capacitance, first thing is, right? However, but the thing is the circuit will be slower actually if I do this, because as the capacitance values get increases, then automatically what will happen? The time charging also will be charged very slowly. Then circuit also will get slow. Then, but what about the good here in the sense? The good compromise is to have equal input and output slope. So because of the cubic dependence, because you might have seen VDD minus 2 VT the whole cube actually, because of the cubic dependence of the short circuit power supply voltage, the supply voltage may be scaled to reduce the short circuit power dissipation. So we can be note that if the supply voltage is scaled down, if the supply voltage is scaled down, means if you like you are having the scaling technique, like one is constant voltage scaling, next is constant field scaling actually. So if supply voltage is scaled down, means if you are reducing the power supply, means such that, how can I say in the sense, your VDD is less than VTN plus VTP, then the short circuit current can be virtually eliminated. Then the short circuit current can be virtually eliminated. So from this I can say, so we can state that the short circuit power dissipation will be depends on short circuit power dissipation is depends on input rise or fall time. That is the first observation we made. The second observation what we made, clock frequency, that is f clock. This will be tau r, tau f. Then third one is CL, that is load capacitance. Fourth one is gate sizes. Gate sizes means W by L, and above all the supply voltage. See, your short circuit power dissipations depends on all these parameters. So like let me show some of the two observations here as I mentioned here. No? So I need to show those observation. The first observation is see this, the first diagram here. Okay, this figure, this is second figure. Okay, you take the first figure here. We are having the VTC, voltage transfer characteristics. of the VDD is greater than or equal to VTN plus ATP. VDD. So now you can see the x-axis is nothing but your input voltage. Okay, whatever we are seeing, this is everything Cmos inverter. This is your output voltage. Now you think first initially here the top what we are having is your we took the threshold voltage. For NMOS the threshold voltage is positive, for PMOS threshold voltage negative. Here 1 volt minus 1 volt. As you know that the formula to choose the threshold voltage is to VT is equal to 0.2 times of VDD. Correct? So here we are taking VD is 5 volt. First you see the VD is 5 volt, then your VTC curve will become like this. Then if the VDD reduces 4 volt, you can see how your curve is shifted towards left. Again the VDD less than 3, again this, again the VDD is less than 2. So almost it's going to become a ideal. See this is equal to 2 Vn. So now at the same time we can see the transfer characteristics, that is VTC. If the VDD is less than, this is your VD is greater than this point, you will get. If your VD is less than the threshold voltage plus the VTP, then what will happen? See this point, this will be your VDD minus VTP, right? This will be your input voltage. So your input voltage first I have said 0, then VD minus VTP. What is the voltage? Nothing but here this is VDD, right? Which is 5 volt. This will be your VTN. The VTN is how much? 1 volt. Then VDD minus VTP minus 1. It's nothing but 4 volt. Example, it is 4 volt. Now we can see up to 4 volt. So here, what will happen? Here the PMOS will be on. P is on. Right? PMOS on. Only PMOS is on in this range actually. So here in this portion, so no transistor is on here actually, this portion. So what we'll get now, this is nothing but your output voltage. As the input voltage we get VD minus VTP, then the output voltage will be increases, only PMOS will be on. Then after that again what happens? Still we are having this way. See this curve? This curve look like you might have seen somewhere else, which look like hysteresis curve, right? In the sense you might have studied in your comparator or in your schema trigger. So similar to like that. So here how I'll get in the sense we'll get like this. It will go in this way. Your transfer curve like this it will come. This is your VTC curve, right? See up to here the PMOS is on. Up to that, see in this place, in this center place here, so no transistor is on, like, or I can see in this place because of VTN less than that, so both the PMOS and the NMOS will be in cutoff region. So the both PMOS and the NMOS is in off condition. So now what happened due to this, I can say here delay will be very high. Delay will be very high. So this is all about the switching. Sorry, this is all about the short circuit power dissipation. Next, what we'll do, let us study about the glitching power dissipation. Next, let us talk about the glitching power dissipation. This is the another one more dynamic power dissipations. Okay. Now, in the power calculations so far, we have assumed that gates have zero delay. Okay. But in real, this in practical, okay, in real, the gates will have finite delay. And this delay will leads to glitch. So there will be some undesirable transition will happen at the output. Those signals only will be known as glitches. Like in the case of static Cmos circuit. So let me take the example better. Okay, let me take the example of realization of y is equal to a, b, c, d, the function that is AND gate. So let me draw the diagram. 4 input AND gate, okay. 1, 2, 3. So now this will be your A, B, C, D. So before considering this, so what I will do, okay, so I don't want to use this. I'll take a simple circuit. Like okay, so I'll take A, B, C. Now this will be your output 1, this will be your output 2. Now what we will do, now I'm going to introduce a delay. The introduce as unit gate means 1 nanosecond, 1 nanosecond. If I'm not introduce any delay, then that will be fine. But you can see I'm going to apply the input as 1, 0, 1. So first A, B will be computed after 1 nanosecond delay only will get O1 output. Okay, correct now? After 1 nanosecond. So I'll say this is input is like this. This will be your input 101. First the O1 output. How will you get to O1? So the O1 output will get as, so initially what will happen? It will be 0, assume as like 1 0 1 0 1. If it is 1 0 1, what is the O1 output? O1 will be 1 0, then that will be 0. So this will be 0, correct? This will be 0. But you can see that 0 will be there for the some period of time because of delay. Correct? There is delta. O1 will be 0. Then after that what will happen? 1 0, the input will be 0 only. But you need to think it will be 0. Till here it is 0. But output will get after 1 nanosecond. But immediately what I am doing, I am going to change the transition from 1 0 1 to 0 0 0. So remember 1 0 triggers to change to 0 0. When it is 0 0, then I will get as output is 1. So now what happened? This is the amount of period it will take to make the output as 1. There will be some delay will be there due to that. Similarly for O2, first initially for 1 0, here I got as what is the value? It is 0, right? But this will be 1 nanosecond. Up to for 1 nanosecond, this 1 also will be there. Now we can say this is 0, this is also 1. What I'll get here? This will be 0. O2 will be 0. O2 will be 0 and that's how it will be 0 O2. So let me draw the O2. It will be, even this also will be 0. O2 also will be 0. O2 also will be 0. Next immediately this transitions happened. You see this is 1 nanosecond. This is another 1 more nanosecond. It will take 2 nanoseconds actually. So means you will get the output this 0 till here it will come. Next what happened? Next will be like 0 0 it has come. So when it is 0 0, so 0 0 I'll get as 1. This also will be 0 1 0, again I'll get as 0. So meanwhile what will happen? The previous output I'll get like this. Then again you will get this 0 is next stage output. This is the previous stage, right? So I can say this will be your glitch due to the timings actually. So the more problem you may face due to this. So this input is 0 0 0. So now what you need to do, like very important, when you're going to using this kind of circuit, the transition will be increases here. The transition increases the dynamic power dissipation, PD, and this component of dynamic power is known as glitch power or glitching power. Next I can say glitching power may constitute a significant portion of dynamic power. So now usually the cascaded circuit exhibits usually, so simply I can say simple, usually the cascaded circuits give high glitching power. So cascading high. So now how to minimize that? So by realizing a circuit by balancing delays. So we need to do the balanced delay. For a highly loaded nodes, for highly loaded, for highly loaded nodes, buffers can be introduced. Can be inserted or introduced to balance delays. So very important thing, you have to avoid the cascade implementation if possible to minimize the glitching power. So example, if you want to say, let me take the example as see now. So this is the figure which I'm showing here. It's a realization of A, B, C, D. A, this is cascade form. This is the cascaded form. This is the balanced realization. How it is, you may think, okay. So you can think, see, here you have to assume as it has 1 nanosecond. It is a unit delay 1 nanosecond. This is also 1 nanosecond. Now, A, B, C, D, 4 input I am applying. Okay, cascade I connected the output to O1, the output to O2, output O3. Now, see, this O2 will execute when the O1 produce the output, then only the O2 will introduce, right? So initially it will be 0 delay, correct? No, 0 nanoseconds. Initially it will be 0 nanosecond. So what will happen? This B will be executed after 1 nanosecond. I will get the output here. But for 0 nanosecond, I am given the input as C. This value will wait until this gate, when it will evaluate, after the 1 nanosecond will get the output. So this input also will be wait for 1 nanosecond. Then O2 will be evaluated. So once the O2 is evaluated, then O3 will be evaluated when after we receive the O2. Means after how many nanoseconds? After 2 nanoseconds. This will be after 1 nanosecond, because this 1 nanosecond will be added with this. Then after 2 nanoseconds, the O2 will get. So the D value will wait for 2 nanoseconds. So now both will be executed at 3 nanoseconds. I get the output. Now I can divide like this. Okay. So now you can see here this portion and this portion. So here 1 nanosecond. This will be 2 nanosecond. So next this portion will be 3 nanosecond. So here what is the critical path? The critical path is 3 nanosecond because it's required 3 nanosecond to get the output in the O3. Okay, now see, I will take 1 nanosecond, 1 nanosecond, 1 nanosecond. Now what will happen? The A, B, C, D. See, this gate also required 1 nanosecond. This gate also required 1 nanosecond. So what I will get? This O1 and O2 output will get when? After 1 nanosecond only I will get. Next, after 2 nanosecond I will get the output as O3 I will get. So what is the critical path here now? The critical path is 2 nanoseconds. See here 3 nanosecond, here it will be 2 nanoseconds. We reduce the critical path. So with the help of this balanced realization, you can reduce the critical path. The delay can be reduced. That is why we said, so we need to add or to insert the balance. In the sense example I can say, it is a buffer second, and even the buffers also can be introduced to make a balance of the circuit. Else, if I do in this way, what will happen? Like say here example I will say in the cascaded form. So here A, B input is given. This AND gate is evaluating. By the time you given the input for C, and continuous the input is there here. What happens? There is a continuous power supply. So what will happen? There is a chances of power dissipation also will be there. Due to that timings, it yields the glitch. So that is why I can say avoid cascade implementation. Or cascade implementation. If possible, to minimize the glitching power. So this is about glitching power dissipation.